We've previously discussed the normal distribution, and we've talked about how it can be used as we can see it coming up in all sorts of places. So if we were to take a sample of people and measure their heights, their weights, their BMIs, all sorts of things. It isn't, you don't see it everywhere necessarily, absolutely everywhere. But you do see a normal, something approximating a bell curve when you do the histograms. When you take a sample survey, you do the histograms, you see these approximate bell curves showing up. Right? So the central limit theorem basically makes this intuition, or this thing that we're seeing, more concrete. Okay, so another example, a lot of theoretical importance here, random walks. So if I were to, I imagine I'm on the number line and I'm walking from integer to integer, right? So I flip a coin. I start at 0. I flip a coin. I move to, if it's an H, I move to +1. If it's a T, I move to -1. Then I flip the coin again. Left, move up or down the integers. Okay? Now I have a histogram which says that after 1,000 flips, how many times was I at 0? How many times was I at 1, -1, n, -n, and so on? And it will turn out that that histogram looks like something that you could fit under a bell curve. So random walks also generate bell curves. Okay, so the central limit theorem is looking at the underlying principle of this. Okay, so what we're going to do is we're going to suppose that we have infinitely many random variables, and they are, we use the abbreviation IID, independent, identically distributed. Okay? So I have infinitely many binomial random variables. I have infinitely many Poisson random variables. But they all have they're the same random variable, they have the same parameters. Okay? I have infinitely many of them. So let's call them x1, x2, that should be a capital X3, and so on. I've got infinitely many of them. So I've got a sequence of these independently identically distributed, it should be, random variables. And because they're exactly the same random variable, they have the same parameters, each one will have the same expectation. Each one will have the same variance. Okay? Now, let's say that I take the sum of the first n of these. Okay? That's another random variable. Now, what's the expectation of this sum? N times mu, the expectation of an individual xi, right? Good. What's the variance?
N squared expectation squared.
N squared times the variance. Yes. Okay. So the expectation of this sum, we said, was n times mu. Mu is the expectation of an individual xi. And The variance would be, well, the individual variances, and some covariance terms, except the covariance terms go to 0, right? So you're going to get n times the variance.
Not n squared?
No. Okay. Not n squared. Okay. So now, what's this? Okay. So now what's the standard deviation? If I have the variance, how do I get the standard deviation? The square root of the variance. So it'll be root of n sigma squared, or sigma times root n. The standard deviation of each one times the square root of n. Okay. Okay, now what if I normalize the sum? So how do you normalize any random variable? What we mean is we take the random variable, we subtract off its expectation, and we divide by its standard deviation. Well, this was the sum of the random variables minus the expectation was n times mu divided by sigma times root n. That gives us a new random variable, and it has an expectation 0 and a standard deviation 1 when you normalize a random variable. Okay?
Standard deviation 1 or variance 1? Or like the same?
Right. So the standard deviation will be 1 and the variance will be 1. Okay? All right. So the central limit theorem talks about what this S hat will be. Okay? So if I've got this sequence of independently, identically distributed random variables, each one has an expectation mu, each one has a variance sigma squared, then this standardized sum, so the sum minus the expectation of the sum, n mu, divided by the standard deviation of the sum, sigma root n, this is going to tend towards the standard normal as n goes to infinity. So if I take the sum of enough independent, identically distributed random variables, then they behave like a normal random variable. Okay? In the limit as n goes to infinity. Okay? So the CDF is given by the probability that this normalized sum is less than or equal to a. That was given by the integrating the PDF for the standard normal from minus infinity to a. Right? Okay. As n goes to infinity, this will be what the CDF for this S hat. Okay. And similarly, the probability that this normalized sum lies between a and b will be approximately given by integrating the PDF for the normal random variable, standard normal variable, from a to b. Okay? As, again, this will be exact as when n gets to infinity. Okay? So this is why the normal random variable is showing up all over the place. Okay, okay, so here's an example. let's say we have average heights of 64 inches. Okay? And so I don't know what the distribution function is for heights, right? But I'm assuming that it's the same for each individual adult woman. Okay? All right, so let's say that then that I take the average, I find that it's 64 inches, I calculate the standard deviation of 3 inches. So what percentage of women have heights more than 67 inches? Well, that means, what's that? What's that in terms of standard deviations?
1.
Right. So how many women have heights which are more than 1 standard deviation from, which are larger, right?
33.
Okay. So, well, okay. So here's my mu. If this is approximately normal, here's my sigma. I'm asked for what's this area under the curve, right? That's what I'm being asked. Okay. Well, I can calculate that as 1 minus this area, and this area would be given by the CDF for the standard normal, evaluated at z equals 1. Okay, so that's the that's approximate, right? So the probability that h is bigger than 67 is approximately the probability that z is bigger than 1, standard normal, which is 1 minus the probability that's less than or equal to 1, and that's 1 minus, I look at the table to find the CDF at 1, and I get this value. That's approximately 16%.
Why is it approximate? Are they not?
Oh, well, because you have exactly the normal when you have infinitely many, when n goes to infinity, right? So before that, it's approximate. Okay. All right. A true-false examination has 48 questions. They're all true or false. Okay. And we haven't studied it all, so we're just going to flip a coin. All right. We'll write true if we get a T, false if we get an H. What's the exact probability of getting 30 or more questions correct? Okay. What's the exact probability?
The binomial for like all of those.
Right, so let's see, there's 48 questions. And we want to get k of them correct, right? So probability of getting k correct, 1/2 to the k and 1/2 to the 48 minus k. Okay, so that's 48 to the k 1/2 to the 48. Okay, and so that's the one, that's for getting exactly k correct, right? And then you're going to go for k is equal to 30. So summation k equals 30 to k equals 48. So that would be the exact way of doing it. And probably you'd need, I don't know, you need a bit of help with a calculator or a computer to do this. And you're going to have issues perhaps with 48 factorials. I don't know how big your big a factorial you can take. Okay? So, we can, as you said, we can do the binomial, right? Okay. Now, what if we wanted to use the central limit theorem? Right? Because the probability getting each one correct, so you can say xi is equal to 1 if I get it correct, and it's equal to 0 if I don't get it correct. Okay? The sum of the xi's is my total number. Right? And then the probability of getting it correct or incorrect, getting a 1 or a 0 is a half each, right? So the random variables, these xi are random variables which are identical, and they're independent of each other. I'm just flipping a coin. The coin doesn't remember what it did last time, right? So they're independent. Okay, so I can use the central limit theorem. Okay, so using the central limit theorem, let me go back to the question. Using the central limit theorem, what would you do?
The expectation of variance goes.
Right. So, let me get an eraser. Right. So now I've got the sum which is correct is x1 plus x2 up to x48, is it? Okay. Now, what was the what's mu here? 24. Okay. Oh, the mu of each individual xi is what? 1/2. What's n here? N equals 48. N mu is the expectation of S. Right? So what's n times mu? 24. Okay. So by flipping a coin, we expect to get 24 correct. The expected number of corrects will be 24. Okay. What's my sigma? Oh, okay, well, what's my sigma squared? Okay, I could get 0 on the question, right? And I could get 0 squared on the question. Sorry, okay. Let me do it in small steps so that I don't make a mistake. Okay. The expectation of xi squared. Well, I could get a 0 squared with a probability of 1/2. I could get a 1 squared with a probability of 1/2. Is that okay? And then that would give me 1/2. Okay? The variance for xi is what then? How do we calculate variance? We take the expectation of xi squared and we subtract its expectation squared. Okay? So it's 1/2 minus this squared, 1/2 squared. So 2/4 minus 1/4 is 1/4. Okay. So sigma for the xi's is 1/2. And what's the sigma for s? Root n. Okay. Okay, so those are the numbers that you're going to need. Okay. All right, so that was the exact one. Okay. We calculated that mu was 1/2. We calculated that the sigma for each xi, sorry, the sigma squared for each xi is 1/4. Okay, so the probability that s is, say, less than or equal to 29 is given by, well, the probability that s minus the expectation of s divided by the standard deviation of s is less than or equal to 29 minus the expectation of s divided by the standard deviation of s. Okay, but when this is your standardized, so this is less than or equal to 29 minus n times mu over root n times sigma, that's 1/2. Okay, so that's exact. Now the central limit theorem says that if my sample was, if the number of random variables was big enough, that will be approximately equal, this standardized sum will be approximately equal to the standard, behave like the standard normal. So this is approximately the probability that the standard normal is less than or equal to this number. Okay? And then we go and we look at our table, or we go online or something. We calculate the CDF for Z, and we get this value. Okay. All right, so let's say the PDC serves 4,000 meals a day. I think it's more now, but let's say it's 4,000 meals a day. 20% of these will include dessert. Okay. Give a range of dessert. So I have to order the desserts, or I have to have the fixings for a certain number of desserts on hand. Right? Now, I don't want to keep too much, because then money will be wasted. I made all these desserts and then I threw them away at the end of the day. Right? Let's suppose they don't keep them for 3 weeks or something. Yeah. Right? Okay. So I want to work out how many desserts I need to order, or whose ingredients I need to have on hand in a day, so that I'm meeting the actual demand 95% of the time. Right? 95% of the time, I want someone who wants a dessert can get a dessert, and I accept the fact that sometimes the demand will be bigger than I expected. Okay? But 95% of the time, I want the person who wants a dessert to be able to get a dessert. Okay. Okay, so now if we look at a bell curve, if we look for this for the PDF, so here's a sigma, here's two sigmas. This is mu minus sigma. Okay, so about 95% of the area under the curve is within 2 sigmas of the mean if we're assuming a normal distribution. Okay, so basically we want to make sure that we're making about these many desserts. Okay, so now in this case, what are our xi's? Well, we can say we have these 4,000 random variables xi, right? Each xi takes the value 1 if the ith meal served has a dessert, or 0 if it doesn't. Total number of desserts is s. Okay? That would be the number of s is equal to the sum of the xi's. Right. That would give us the total number of desserts served in a day. Okay. Okay, now we assume that the xi are identically distributed, right? And we assume that they're independent. Is that always a good assumption? Well, okay, so, right, sometimes people are coming in with their friends to eat lunch at the same time. They may be influencing each other. So maybe, but okay, we should be conscious of our assumptions and we should be conscious of when they might go wrong. Okay. All right. Okay. So the expectation for mu for each xi is given by what? Well, 80% of the time there's no dessert. So 0 if you have a dessert, 0 if you don't have a dessert, 1 if the ith meal has a dessert. 80% of the time, by historical data, we know that the meal will not have a dessert. 20% of the time the meal will have a dessert. So the expected value for every single xi is 0.2, because we're assuming that the xi are identical. Okay, the variance of each xi. Well, that'd be 0 squared times 0.8 plus 1 squared times 0.2. That would be the expectation of xi squared. And then we subtract off the expectation for the xi, and we get 0.16. Okay. All right. Then the expectation of the sum is n times mu, so there's 4,000 desserts times an expectation of 0.2, which was 800. Okay. Sigma, the variance for the SI we said was n sigma squared, right? So 4,000 times 0.16. And then we take the square root of that. We'll get that the variance for the number of desserts is 25.30. Okay, is that okay so far? Okay. So that's the variance. That's the standard deviation. So if we want to have 2 standard deviations more than the expected value, that would be 50.6. So if we have 50.6 desserts, as the standard as 2 standard deviations, then 95% of the time, you know, the actual number of desserts served, or the actual number of desserts desired, 95% of the time, it will lie between 2 standard deviations from 800. So it'll lie between 749 to 851. So 95% of the time, the actual demand will lie between 749 to 851. So how many desserts should we be prepared to make?
800 minus 50
Well,
and 800.
yeah. So I would say if I make 851, at least I have the preparations for 851. Then I've got even more than a 95% chance that I can meet the actual demand. Okay. So that was why that was a discussion of why the normal distribution shows up everywhere and how we can use that information. A little while later, we'll see that there are important things which are not described in the same way. But this works a lot of the time. Okay. Any questions about that? No. All right. See you on Thursday.